Hello, students. I've prepared this video to respond to the exercise that you just concluded. So I'm doing this video hoping that all of you have has made an attempt to submit the exercise, because by the time I upload this video, I'll not be accepting any more submissions of the same. I'm referring directly to the data communications class, and the question is on reinforcement learning and Markov decision process. Now, the question reads: a robot moves in a 3 by 3 grid starting at 0, 0, which is the origin. Now, the rewards are, it is positive 10. The reward is positive 10 at the node 2, 2 in the 3 by 3 grid. Otherwise, any transition which does not result the robot to node 2, 2 results in a penalty per move. Now, transition probabilities are uniform, meaning that at any point that the robot is, it can take any direction with an equal chance. Now, compute the value function, that is the V of S for 1, 1, for the node 1, 1, where S is 1, 1, assuming that this symbol that looks like Y is 0.9, and the symbol here represents a discounting factor. Now, the significance of a discounting factor is that it gives more emphasis to the current action than to the future action. Now, let's see very quickly what the grade would look like, so that even as we set out to look at the solution, then we already have an idea of what we are dealing with. So consider this. Let's consider this is the grid. Yeah, it's a 3 by 3. So I would call this, let me call that 3 by 3. It's 3 by 3. So I'll solve this. I'll solve that. So definitely this is 0, 0. This is 0.00. This is the origin. It's actually the 0.00. This will be the 0.01. This will be the 0.02. This will be the 0.10. This will be the 0.11. This will be the 0.12. This will be the 0.20. This will be the 0.21. This will be the 0.22. So we see that in the entire transition of this particular robot, our main concern is to consider, because we are told that we need to get the V of S, where that V of S is 1, 1, 1, 1, 1, 1, like that. It's 1, 1. So it's at this point. It's at this point here, this point. Just a moment so that we are clear about it. This point is 1, 1, meaning first row, first column. That's where we are. So we are starting from this point. And you see that when we are at this point, when this robot is at this point here, it can visit state 0.1 by going up, or it can go to the left where it lands at cell 1.0, or it comes from 1.1 to 1.12, or it comes from 0.11 to 2.1. And either way, it can move with equal probability. So it means that moving from here to here is a quarter. The chances are quarter, the chances are quarter, the chances are quarter, the chances are quarter. But by the time a decision is made that now it's moving this end, then it's moving there with certainty, and the probability is 1. So that is the equation that we had, as we had briefly seen. Now let me set out on the board to see how we are expected to solve it. Welcome to yet another session, and my focus will be to consider the exercise that in my last class, that is the data communications class, there is an exercise that had left about in an reinforcement learning, and I want to look at it hoping that all the students have submitted the work so far. So we say, the question read, a robot moves in a 3x3 grid, starting at the origin, that is 0, 0, and rewards are 10 at the point 2, 2, node 2, 2, and there is -1 per move that is made. We are told that transition probabilities are uniform. Now, the question is compute the value function for the node 1, 1, assuming y, which is the discounting factor, is 0.9. So first, let me draw it. It's if we are talking about a 3x3, then we should be considering something that looks like this. Yes, something that looks like this. So that I have here. No. I have this. Yes, I have that. And then I also have this. I also have that. So these are 3x3. 1, 2, 3, 1, 2, 3. These are 3x3 grid. And we can name this, if we consider this to be, so what we would say is that we refer to this as the origin. This would be the position 1, 1, and then this is the position 2, 2. So what that would mean is that I have here 2, 2. I have here 2, 1. Yes. These are the nodes. I'm defining the nodes. Then here, 2, 2, 2, 1. Then here, 2, 0. And definitely, if that's the case, then here would be 1, 1. Because it's column 1, row 1. It's row 1, column 1. So that means that we would have the origin to be here 0, 0. Then here to be 0, 1. Here 0, 0, 0, 1, 0, 2. Then this will be 1, 0, 1, 1, 1, 2. And this is 2, 0, 2, 1, 2, 2. So this is the origin. Yeah. So if that's the 3x3 grid that we have, so I was just I was trying to give reference to the cells. So this is cell 0, 0. Definitely that's the origin where the work would start. But here we are asked to calculate the value function at this particular point. This point here, because what we want, the question had required us to get the value function s, and that occurs at 1, 1. That's what the question specified. So what then we do is, and the discounting factor is also given us. Discounting factor is also given us 0.9. 0.9. That's the discounting factor. So to compute the value function, that is this. Yeah, because we are asked to compute the value function for that particular node. So to get it for the robot at this particular point, then we would use what we refer to as the Bellman equation. We introduce the Bellman equation to help us quantify the value function in each particular step that can be taken. Now, another thing that I ought to mention, that I should mention now, is that the reward, according to the definition, we are told that a robot moves in a 3x3 grid starting at 0, 0. Now, rewards are 10 at 2, 2. So it's only here that we have a reward of 10. Yeah. Otherwise, what we have is that there is a penalty of -1 per move. So if that's the case, then we are definitely going to say, well, we can start with that anyway, because starting from here, one, yeah. So -1, -1, -1, -1, -1, -1, -1. Now, the only node that has a reward is node 10. So we use the Bellman equation, that is the Bellman equation. We use the Bellman equation, and we use the Bellman equation for the value functions in a Markov decision process, in a Markov decision process. And the value function will be defined, we'll define the value function as, here we have, it is summation that is for actions A, where we have this, and it's action, that action given the state. And again, we have it, summation, that is of visiting the next state, the probability, that particular probability that you are in the next state, given that was you have left the current state, having taken action A. And I have the line here, but I want us to ignore this line because our equations are long. They are going to be longer. So this line, yeah, let's just retain it for now, but I'll be overlapping. So what it has again, the other bit is this, where now we say R into S A S prime plus this plus that into the value function in the next step. Yes. So this entire equation, this gives us the value function, this particular equation as we see it. And here, S represents the current state. And the current state in our case is 1, 1. So we should be starting at position 1, 1. So current state is 1, 1. And possible A here stands for possible actions that one can take. Because if you are starting at node 1, 1, if that robot had moved, and at this particular point, we realize that the robot is in node 1, 1 or cell 1, 1, then there are possible steps that the robot can take. The robot can either go up to node 0, 1, or it goes right to node 1, 2, or it goes left to node 1, 0, or it goes down to node 2, 1. So those are possible actions that the robot can take. So anytime it is found to be in this particular state, then it is known that it is likely to move in either of the four. And that's what is represented by A. So possible action. Now, S prime here should denote the next state after taking action A. Meaning, if it was here, then we find it here. Then the action we are referring to is that of going right. Then all of this pi and that in bracket, it refers to the policy. And policy here is assumed to be uniform, that is of having equal probability. Since you see, if the robot is at this particular point, I've denoted it by X. It's a big X, but it should not confuse. Let me just put it a star so that it refers to the point of reference, not necessarily X. So there is an equal opportunity. If the robot is here, it can move left with a probability a quarter, or up with a probability a quarter, or right with probability a quarter, or down with probability a quarter. So that's what we mean here by uniform probability for all actions. Any action taken, and that is represented by this. That is represented by that. Then we have this particular part here. We have this part, because I'm now trying to make sense of what the formula is. So this one here, this refers to the transition probabilities. And transition probability is just that if for some reason it had chosen the action of moving from 1, 1 to 1, 2, then what is the probability of it going back, going up, or coming down? We still find that that probability again is equal. Those probabilities are equal. So there'll still be a quarter. So it's 1 over number of possible transitions. So it becomes 1 over 4. So that is this. That is this. But now let's see what now this is. This particular part is, this is A. This is A. I think I should write it clearly so that it's clear. Yeah, that is A. So it means reward. So if I had to move from node 1, 1 to node 1, 2, my reward is -1. And that's particularly what it represents. That it represents the reward for moving from state A to state S prime, having taken action A. And we see that in the grid, it's -1 except at the point 2, 2, at the node 2, 2. So that's what is represented by this. Now I come to this particular part of the formula. This is the discounting factor. This here. It tends to give more importance or relevance to less importance to future results, but gives more weight to current results. And that is what makes it more practical. So, and this simply means if this represents the current state, then this should represent the state that you are yet to visit. So that's basically what all this particular part. That is what the Bellman function, the Bellman equation is referring to. So it's a Markov decision process, because you see the switching patterns that we are employing as we go along. So what then we do is that now we have seen that it's only here that we have a reward of 10. Anywhere else, there are penalties. So we see that the reward that we have is only at the node 2, 2, where we have 10. But any other place, this assumes the value -1. So let's define transition probabilities and actions. Because one, just like I'd said, the possibilities that we have is that if we are standing at node 1, 1, then you can only go up, or go left, or go right, or come down. Those are the 4 possibilities with equal probabilities, which means that the chance of each is a quarter. So since the transitions are uniform, so that means that this particular part of the equation, this part will be a quarter. And so the immediate reward, what we have is that now we want to change this into, this is the general Bellman equation. But now what I want to do is to make it specific to our problem, which is this. So if I do that, then it means that I'm going fast. What I can change here is instead of writing SS, then let me now be specific and call it 1, 1. So V11, value function at the node 1, 1. Then once we have that, with uniform probabilities, if probabilities are uniform and we had defined this, we defined that this particular part, this part here, we defined it to be policy, which is assumed to be actually equal probability of actions. That is, action, the weight of an action given a particular state. And we are told that in this case, we consider it to be a quarter. It is uniform. So this is a quarter. In that case, that's a quarter. Then that allows us to says that is uniform probability. And again, we also see that, then we are left with this. So in this case, if this for a valid probability, if you sum all this and each is a quarter, then it means that the whole of this, the entire this, because it's a quarter and you are summing every time, it means a quarter plus a quarter plus a quarter will give you 1. So this will be, that will be 1. So let's try to substitute that particular argument into this and see what we are left with. So I'll be having V11 is equal to, I've said this should be a quarter. That should be a quarter. If we consider this, then this should be a quarter. We then say a quarter. And since this is 1, then it means that having said a quarter, then the summation we are having should apply. This summation here should then apply to what is inside that particular bracket. And so we will be saying here, because this is a quarter, the whole of this is a quarter, the whole of this is 1. So I'll be having a quarter, and we are summing in the neighborhood. We are summing in the neighborhood of the step that we have taken, on the step that we have, on the cell that we have landed, the robot has landed on, given that it has taken action A. So, so here we'll be summing over the neighborhood of this, and it will be its neighborhood of 1, 1, because that's where you are. Neighborhood of 1, 1, because that's where you are. Then we'll be looking at this, and we know that the reward at any point which is not 0.22 as attracts a penalty. So here first what we'll be having is -1, which is the penalty, plus that something that which looks like gamma, we'll call it actually it's 0.9. We are given it's the discounting factor, this. Then what the value should be when we get to that next step. So I'll just write it as that for now. I'll write it as such. So this is what our Bellman equation has reduced to. The Bellman equation has reduced to this. So we then want to substitute values. Then we get what the value function at this particular node should be. So what we do, we already know the neighborhood or the neighbors of the values. We know that the neighbors of 1, 1, I should write them somewhere. Neighbors of 1, 1, I should say is 0, 1. The other neighbor is 1, 0. The other neighbor is 1, 2. And the other neighbor is 2, 1. So those neighbors those are the people. Actually, those are the cells that the robot can visit once it finds itself in state 1, 1. So these are the neighborhoods. Now I want then to sum to give that particular to sum under that. So we'll assume initial estimates for VS prime. We'll assume initial estimates for VS prime, which is given through iterative policy evaluation. So suppose what we have is that suppose the value function at this node we give as negative 2.0, and then the value function at this node, because initial values must be given. That's the initial condition must be given, so that because by the time it's at that point, there are what we refer to as initial values, because we have already observed what the system is. So this will be, if this is assumed to be negative 2.0, and this is 0.5, and this is negative 2.0, and this is negative 1.0 as such. So we assume those are the initial value functions, initial estimates of the value functions. Then what we will have, we then have to substitute them in this equation. So yeah, we'll substitute it in that equation. So that's what we have here is this. Did I have all of them? No, it should be this. Should be that. No, it's the prime refers to the S, which is the state that is visited. Yeah, so it's just this. I don't have to include the prime. The prime simply means step that it visits, when the next step that it visits whenever it moves from a particular point. So if these are the estimates that we are given, then we are able now to estimate what this may be. So to estimate what this may be, we again say this is a quarter. But then, here, that's what we have. So once we have that, we start with the first case. First case would be where it's negative 1 plus 0.9 times 0.9 times negative 2.0. Negative 2.0. I think I should use this so that there's a difference. Let me use this here. Plus negative 1. Again, let me put this. Negative 1 plus 0.9 times 0.5. Times 0.5 plus, yeah, let me bring it here, plus plus, let me just have this, plus negative 1 plus 0.9 times negative 2.0. Then plus, again, negative 1 plus 0.9 times negative 1.0, like that. Then I have this. Now, if you sum this, you'll then, so it means you'll have to multiply, get these products, sum them, then divide them by 4. If you do that properly, with a lot of keenness, what you should get is negative 2.0125. Negative 2.0125. So the value V11, that is at that point, negative 2.0125, indicates that the expected cumulative discounted reward starting from 1, the cell 1, under the given policy and transition probabilities that we define to be uniform, is approximately negative 2.10. This reflects the penalties incurred by moving and the eventual reward at the node 2, 2. Now, why is the not why this here? It looks like why can call it lambda. Well, I don't know the right symbol how to call it, but it is the discounting which ensures that future rewards are given less importance compared to immediate rewards. And this model, that particular argument models real world where immediate actions are typically more impactful. And so that is what I expected you to do. So if at all in the course of going through your assignment, you kind of mentioned the Bellman equation, then I would want to see how you get your transition. I want to see the element of the MDP by having to transition from 1 to either of the positions that we have said. And then by looking at the value functions, then this is what we may settle on if at all we started here. Because if the robot is here, if it's a game, the robot does not have emotions. It knows that it has equal chances. And we see in that particular case, it can move. If it's here, it may move from here. If it were to make the right decision, it would be biased so that it moves from 1 to say 1 2, then get the reward. But that's not what it is. Then, if it had emotions or biased, then it would also decide that now I come from 1 I go to 2 in which case there's only a penalty of -1, then I get the reward. But you see, being a robot and the chances are equal, at any point it can take any particular walk. When it's at 1 it can go here. It can come here, then it may visit many states before it gets the reward. So that's why we are saying the value function at that particular point, if we start here, is likely to be this. Now, in my next video, I'm going to look at it will be a continuation of this, but now what I'll be looking at is how to calculate or compute the gradient of the value function at any point S. Does not necessarily need to be 1 at any point S in a n by n grade or a 3 we'll be considering 3 by 3 grade because that's what we had started with. So up to now, look out for my next video where I'll be giving a solution first on how to compute the gradient, because to compute the gradient you will have to get to differentiate this function here, the Bellman function. It has to be differentiated. That is what will lead us to the right answer. So up to there, I urge you to be keen to follow my next video.